Jai Hind students, welcome to my YouTube channel. Today we are going to discuss the grouping or rather the combination of cells. So we will be discussing three topics in this particular session. The series grouping of cells, the parallel grouping of cells and the mixed grouping of cells. And in each of these three topics we will try to find out the condition to derive maximum current from these grouping of cells, right? So let's begin with the first article, which is the series grouping of cells. So let us consider n cells. All are identical to be connected in series, and they are connected in such a manner so as to send current in the same direction through an external resistance capital R, right? So we'll consider n identical cells, each of EMF E and having internal resistance R, all connected in series in such a manner so as to send current through an external resistor in the same direction, right? This is the external resistor of resistance, say capital R. This is the external resistor offering resistance capital R, and all the cells are identical. So all the cells are offering internal resistance smaller. Each cell is of EMF capital E. So they are identical, and there are n such cells. There are n such cells. Right, students? And these cells are connected in such a manner so as to send current in the same direction. So obviously all the cells are sending in a current in the anti-clockwise direction, right? So net current flowing through it is represented by capital H of I. So all the EMFs will get added up because all the cells are sending current through the external resistance in the same direction. So it can be simplified. The circuit can be simplified. It is equivalent to a circuit comprising of a single cell of EMF, net EMF. As I told you, all the cells are connected in such a manner so as to send the current in the same direction. So net EMF will get added up. So what will be the net EMF then? Net EMF, it will be given by E plus E plus E. N times, N are the total number of identical cells connected in series. So it will be equal to N times E. So this circuit can be modified in this particular manner. It can be considered to be having a single cell of EMF capital N. Now what about the net internal resistance? Let's check it out. Now all these are connected in series, and in the series the formula is R net is equal to R plus R plus R. Again N times. It is N times. So what you get is N times internal resistance of a single cell. So this is N times smaller. Right, students? And this is the external resistance. So this is the net current. So this circuit can be modified or redrawn in this particular manner. Right? Now let's determine the current in the circuit. In any circuit, current is given by net EMF divided by net resistance. Net resistance, students, it will be the sum of the external resistance and the net internal resistance offered by the source, right? So the net current flowing through the circuit, it will be given by net EMF divided by net resistance, which will be equal to net EMF is N times E, isn't it? Divided by net resistance, it would be external resistance, which is capital R, plus net internal resistance, that is N into small r. So I is equal to NE divided by capital R plus NR. So this is, now let's consider the special cases. Now let's consider the case 1. When the net internal resistance is very large as compared to net external resistance. I mean, we are dealing with the case whereby the net internal resistance is very, very large as compared to the net external resistance, or the net external resistance is negligible as compared to the net internal resistance. So in such a case, what we can do is R plus NR. Since R is very, very small, therefore R plus net internal resistance, it will give us approximately net internal resistance. Right, students? So substituting this value over here, we get current in this case would be equal to NE divided by NR, which will give us E by R. Isn't it? So this is the case where we have considered the net external resistance to be negligible. So R can be neglected in comparison to N into smaller, which is the net internal resistance. So the current in this case would be NE by NR. N get cancelled, we will be left with E by R. Now look students, E is the EMF of a single cell. R is the net internal resistance. External resistance is negligible. So E by R would be the current due to a single cell. So even on connecting n number of identical cells in series, and if this condition is satisfied, then we will be getting current which will be only equivalent to the current due to a single cell. So it is but obvious that this situation is not at all preferable, isn't it? So let's consider the other scenario. Now let's consider when the net internal resistance is negligible as compared to the net external resistance. Now, net internal resistance being negligible, NR can be neglected. Therefore, R plus NR may be approximately written as R. So in such a case, the current would be equal to NE. Here, the internal resistance is negligible, so we'll be left with NE divided by R. This NR is very, very small, infinitesimally small as compared to the external resistance. So it can be neglected. So we'll be left with only R in the denominator. So it will be equal to N times E by R. So this is the current due to a single cell, isn't it? Internal resistance is very, very small, so it is neglected. So E by R would give us the current due to a single cell, and N times. So here what we get is N times the current due to a single cell. So you can easily judge from these two cases that which one is preferable to obtain maximum current from this circuit. In case this condition is satisfied where external resistance is negligible as compared to the net internal resistance, then we will obtain current only due to a single cell. And in case the internal resistance is negligible as compared to the external resistance, then we will obtain current which will be given by N times the current due to a single cell. So obviously this is the preferred situation, right? So what's the conclusion? In order to derive maximum current from the series grouping of cells, the net internal resistance offered by the series grouping of cells must be negligible as compared to the net external resistance. So by satisfying this particular condition, we can derive maximum current from the series grouping of cells. So students, this first article regarding the series grouping of cells is over. Now let's try to concentrate on our next topic, which is the parallel grouping of cells. So we'll consider the same intro, that is, we have considered n identical cells. All cells are identical, each of EMF capital E and having internal resistance smaller are connected in parallel, and an external resistor is connected across the combination, and all the cells are connected in such a manner so as to send current in the same direction through the external resistor. So this is the diagram. These are the n cells which are connected in parallel. And all the cells are identical. All the cells are identical. Each of EMF E and each having internal resistance of R. Each having internal resistance of R. and this combination is connected across an external resistance like this. This is capital R. And all the cells are sending current in the same direction, right? So the net current is I, net current flowing through the resistor capital R is R, isn't it? And let us consider these to be N cells which are connected in parallel. Clear, students? Now here also, as was done in the previous case, we will try to simplify the circuit. Now students, you are aware of the basic concepts. In series, the potential difference get added up, but in parallel, the potential difference is same. All the cells are connected between the same 2 points A and B. So all the cells being identical, the net potential difference across AB would be equal to the potential difference across each of the cells, isn't it? So your potential difference will remain constant. So what is net EMF? It will be equal to E, because in parallel the net potential difference is constant. All the cells are identical. So net potential difference is E. And these internal resistances, they are connected in parallel. So let's try to find out the net internal resistance in the parallel grouping of cells. So in the parallel combination, this is the formula which we make use of. 1 by R net would be equal to 1 by R plus 1 by R and so on. It will be N times. It will be N times. So what you get is N by R, which implies that net internal resistance would be equal to R by N. Is this clear, students? So now what we can do is we can modify the circuit and we can redraw the circuit in this particular manner. All the cells can be replaced by a single cell of EMF E, net EMF is E, and having net internal resistance of R by N, and it is connected across an external resistance capital R. This is the current which is flowing through the external resistor. Clear, students? So this entire circuit can be redrawn in this particular manner. So net current, as we are aware, in any circuit the net current is given by net EMF divided by net resistance. And net resistance, students, it is the sum of the external resistance and the internal resistance, right? So net current flowing through the circuit would be given by net EMF divided by net resistance. Net resistance is the sum of external resistance and internal resistance. So net EMF is E, net resistance is external resistance plus internal resistance, R by N. So current is equal to E divided by R plus small r by N. So this is the expression for the current in a circuit comprising of N identical cells which are connected in parallel. Now here again let's consider two cases. Case 1. Suppose when R is very, very large as compared to R by N. R by N is the net internal resistance. In such a case, R plus R by N may be approximately equivalent to the R, because the net internal resistance offered by the parallel grouping of cells is considered to be negligible. So in such a case, current would be given by E divided by capital R. R by N is very small as compared to capital R. So R plus R by N may be roughly equivalent to the R. So current in this case is E by R. E is the EMF of a single cell and R is the external resistance. Net internal resistance is negligible. So E by R would give you the current due to a single cell. So this is current due to a single cell. So in the parallel grouping of cells, if the net internal resistance is negligible as compared to the external resistance, then we'll be able to derive the current which will be only as much as equal to the current due to a single cell. So obviously this situation is not at all preferable. Obviously we would want to derive maximum current from the grouping of cells, isn't it? So let's discuss the other case. When R is negligible as compared to R by N. So here we are considering the case where the net external resistance is negligible as compared to the net internal resistance. So in such a case, R plus R by N, here it will be R by N because capital R, which is the net external resistance, can be neglected in this case. In such a case, the current would be given by EMF E divided by R can be neglected because R is considered to be extremely small. It is vanishingly small as compared to R by N. So we'll be left with R by N, which in turn would give you N times E by R. Here the external resistance is negligible. So E by smaller r would be the current due to a single cell. So here what we obtain is N times the current due to a single cell. So look students, if in a parallel grouping of cells, if this condition is satisfied, then the current obtained from the circuit is N times the current due to a single cell. So obviously this condition is preferable. So what's the conclusion? In order to derive maximum current from a circuit involving parallel grouping of identical cells, the net internal resistance should be very large or the net external resistance should be negligible as compared to the net internal resistance offered by the parallel grouping of cells. So that's the conclusion. In order to derive maximum current from a circuit involving parallel grouping of cells. Right students? So the conditions for series and parallel grouping of cells for deriving maximum current from the circuit are exactly opposite to each other. In series, in order to derive maximum current, net internal resistance should be negligible. In the parallel grouping, in order to derive maximum current, external resistance should be negligible. Right? So we have done these two articles. Now we are left with the mixed grouping of cells. In the mixed grouping of cells, students, what we will do is, we will consider again n identical cells. Again, each cell of EMF capital E having internal resistance small r. But here, we will consider the case of rows and columns because some of the cells are connected in series and some of them are connected in parallel. So what we consider is, we are dealing with the mixed grouping, means series as well as parallel grouping, right? So let's consider this case. These are the cells which are connected in series. So this is the branch containing cells connected in series, and as we have considered each cell is identical. So all of EMF capital E and internal resistance smaller. And we'll consider such many branches to be connected in parallel like this. All are identical. So this becomes the mixed grouping of cells. This becomes the mixed grouping of cells. And all these cells are connected in such a manner so as to send current across the external resistor in the same direction. This is the circuit. Suppose this is the external resistor. So all these cells are connected in such a manner so as to send the current in the same direction through the external resistance. Right? All the cells are identical. Let us consider there are m rows. There are m rows, and each row contain n identical cells, small n identical cells. Right students? All the cells are identical. It's understood. All the cells of EMF E and all the cells have internal resistance smaller. So this is the mixed grouping. So now what we intend to do is, we'll try to simplify the circuit. We'll replace all these cells into a single cell, right? Let's do it. So it's equivalent circuit. Look students, in the series grouping I have told you, all the cells are identical. All the cells are sending current in the same direction. So their EMF will get added up. So what is the net EMF in each branch? it will be equal to n times E. There are n cells. There are n cells connected in series. So in series the EMF will get added up. So what you get is each cell will have EMF E. So in each column, in each row actually, the net EMF will become n times E. And what about the net internal resistance? Again, in this row, all the cells are connected in series. Therefore, the internal resistance will also get added up. R net would be equal to R plus R n times. So it will become NE. In fact, NR. R is the internal resistance of a single cell. So there are m such rows. Each row will have a net EMF of NE and net internal resistance of NR. So the circuit can be modified in this particular manner. This is NE, net EMF of each row, and net internal resistance of each row would be NR. And there are m such rows. There are m such rows. And this is connected across an external resistor. This is it. And it is sending current in the anti-clockwise direction through this external resistor. Clear, students? Okay. Now still the circuit can be simplified, right? Okay, let's see. All these cells, which are m times, they are connected in parallel. And students, in parallel, the potential difference is constant, isn't it? So all these cells can be replaced by a single cell having net EMF of NE and having net internal resistance given by, let's try to find it. How to find the net internal resistance? All these are connected in parallel. So 1 by R net would be equal to 1 by NR plus 1 by NR plus 1 by NR. How many times? M times. There are m identical rows. So this is m times. So what you get is m by NR. So 1 by R net is m by NR, which implies that net internal resistance offered by the mixed grouping of identical cells would be given by NR divided by m. Right, students? This is the net internal resistance. So R net internal resistance is NR divided by m. Clear? So we can replace the entire cells into a single cell. So what we obtain is this circuit. So now the circuit gets simplified. Right, students? The entire circuit is modified in this simplified form. Clear? Now, as was done in the previous two articles, we'll try to find out the expression for the current flowing through the circuit, and then we'll try to find out the condition for extracting or for deriving maximum current from this mixed grouping of cells. So let's do it. So net current in any circuit, as you are aware, it's given by net EMF divided by net resistance. So what we do is net current through the circuit. It is as usual given by net EMF divided by net resistance. Net resistance, students, it is the sum of the net external resistance and the net internal resistance. So net EMF is NE. Net resistance is sum of external resistance and the internal resistance. Net external resistance is R. And net internal resistance is NR divided by M. Is it clear, students? Now we need to express the current in terms of the total number of cells, right? Now there were m rows and each row contained n cells. So total number of cells, which is capital N, it will be given by m multiplied by n, isn't it? So let's try to express current in terms of the total number of cells. So how to proceed like? So what to do is, let's take LCM, it will be m, over here it will be mr plus nr. So what we get is MNE divided by MR plus N into small r. Clear, students? So now what to do is Mn, as I have told you, it will give us the total number of cells in the mixed grouping. So we get N times capital E, this is capital N, which is the total number of cells in the mixed grouping, divided by Mr plus Nr. So this is the expression for the current which is flowing through the circuit involving mixed grouping of identical cells, right? Now, in order to find the condition for maximum current, there are two ways. One is by using calculus method, right? For I to be maximum, the denominator must be minimum. And for the denominator to be minimum, the first derivative of this denominator should be equivalent to 0. And then we can easily get the condition. Other method is to get the condition for the maximum current without using calculus. Especially it will be useful for the medical students. So I am using that simpler method. So here it's very clear. For current to be maximum, for I to be maximum, the denominator that is, what is the denominator? That is Mr plus Nr should be minimum. It should be minimum, right? So here it's pretty clear. For current to be maximum, the denominator it should be minimum. Now, when the denominator will be minimum, let's see. A plus B, students, it can be written as root A minus root B whole square plus 2 root A root B. Isn't it? This is a formula you must be aware of. If you solve it, you should get A plus B only. Suppose A is Mr and B is Nr. So accordingly, Mr plus Nr can be expanded by using this formula. So what to do is Mr plus Nr, it can be written as Mr square root of Mr minus square root of Nr to the whole square plus twice square root of Mr square root of Nr, like this. Just using the above formula, Mr plus Nr can also be written in this particular manner. Clear, students? A plus B is equal to root A minus root B whole square plus 2 root A root B. So what I have done is, I have expanded Mr plus Nr in the above form. Now look, this is in the form of A minus B whole square. For this to be minimum, this term needs to be minimum, right? For Mr plus Nr, that is for the denominator in this expression to be minimum, the term Mr minus square root of Nr whole square, it should be minimum. And what is the minimum of any whole square value? It is always 0, because whole square, it can't be negative. So this term will have a minimum value of 0. That is, for Mr plus Nr to be minimum, square root of Mr minus square root of Nr to the power whole square, it should be equal to 0. Right? Let's try to solve it now. Take square root on both sides. What do you get? It implies that Mr minus square root of Nr is equal to 0, which further implies that square root of Mr is equal to square root of Nr, which further implies that Mr is equal to Nr. That is, R is equal to Nr divided by M. This is the condition, students. Now remember, what is Nr by M? Nr by M is the net internal resistance offered by the mixed grouping of cells. So, what's the condition? Net external resistance is equal to net internal resistance. So this is the condition which needs to get satisfied so as to derive maximum current from the mixed grouping of identical cells in a circuit. Clear, students? So I repeat, in order to derive maximum current from the mixed grouping of cells, the net external resistance of the circuit must be precisely equal to the net internal resistance offered by the mixed grouping of cells. So that completes the third article as well. Now let us try to revise the conclusion, revise the results in each of these following three topics, right? So in order to derive maximum current, in the series grouping, net internal resistance should be negligible as compared to the net external resistance. This is in the series grouping, right? This is the condition for obtaining maximum current. In the parallel condition, the condition will get reversed. In this case, the net internal resistance should be very, very large as compared to the net external resistance. It should be very, very large as compared to the net external resistance. And in the mixed grouping, in order to derive maximum current, the condition is net internal resistance must be exactly equal to the net external resistance. So these are the conditions for obtaining maximum current in the series, parallel and mixed grouping respectively. So students, I hope that you have understood the concept clearly. We have done the mathematical verification in order to derive these conditions, right? So before attempting the numericals based on these topics, you are supposed to retain the results. They are very, very important. In numericals, you will be directly using the results which you have derived in the theoretical portion. So students, do revise this topic and we'll continue in the next lecture then. Till then, goodbye and do take very good care of yourself. Thank you.